Hello everyone, our 12th tutorial class. In this class, we will be studying plasma technology for industrial applications, options, efficacy and benefits. So here you go, plasma and industry, electronic industry, the application is etching, deposition, cleaning. Then the type of plasma you are usually using is radio frequency, inductively coupled plasma and microwave plasmas. In textile industry, we are using plasma for surface activation, dyeability improvement, and usually the type of plasma you are using dielectric barrier discharge and cold plasma. In automotive industry, we are using this plasma for surface cleaning, bonding preparation. We are using atmospheric pressure plasma devices. In biomedical, we are using for sterilization, coating implants, we are using cold plasma as well as electron cyclotron resonance plasma, specifically in the coating of these bioimplants. Now, in case of energy sectors, we are using plasma for waste to energy, gas reformation, and usually we are using arc plasma, radio frequency plasma and microwave. In metallurgy, we are using plasma for plasma spraying, coating applications and for refining metals, and we are mostly using thermal plasma. So what you can see from this slide, that plasma is covering a very vast variety of industries. Electronics industry, textile industry, automotive industry, biomedical industry, energy sector, metallurgical industry, all of them are using very effectively different plasma technologies. Radio frequency plasma, inductively coupled plasma, microwave plasma, dielectric barrier discharge, electron cyclotron resonance, arc plasma, all of these are nowadays very essential element of this technological advances. Now, the benefits for which the industries are oriented towards plasma is that many of the cases they are offering one step process replacing the multi-step wet chemical routes, and they are environmental friendly because they are not producing the kind of effluents that usually encountered in competing other processes. So they are environmental friendly, reduces need for chemicals. Apart from that, many of these processes requires actually sufficient time for startup and shutdown. But most of the plasma devices are immediate startup and immediate shutdown, especially those which are being done at atmospheric pressure. For those systems which require vacuum, of course, you need some time to reduce the vacuum level to the value where you want to operate. But in case of atmospheric plasma like thermal plasma or atmospheric cold plasma devices, you can just immediately switch on and immediately switch off. Precision control is one of the things where these CCP devices are doing a great job. They can do the etching for very delicate electronics and in a very precise manner. As far as the versatility is concerned, you know that plasma is applicable starting from ceramics to non-conductors to metallic, anywhere, everywhere almost, it has extended its potential. Now, as far as efficacy is concerned, you know that um, it can speed up process by imparting its effectiveness through the ions and atoms, nascent atoms, which has been produced. As I have always told in the regular classes that a reaction which you know um, happens at a very very slow rate when the molecules are present, the same reaction can happen at a much faster rate when atoms are present, and the same reaction can happen much faster rate when you are using ions to do the same reaction. So because plasma is inherently a system which contains very high energy species, so this kind of reactions which are not otherwise attractive can be very attractive when you are going for plasma systems. So that is the key of the efficacy which is achievable from plasma devices. Now, plasma in agriculture, that is one thing that is not covered in our earlier tutorials, I cover it here. So, synthesis of nitrogen fertilizer is one of the things. Plasma activates its nitrogen and oxygen from air to form NOx, which dissolves in water and form nitrates. This is a simple sentence, but this is not so simple when you go to do the actual things, because you know the triple bond of nitrogen, it is so strong, it is very difficult to break. Plasma is having the potential, because of its very high energy, it can break the bond. So in nature, the nitrogen bond is broken by the lightning, which is again a plasma. So plasma is specifically suitable in this area because this strong triple bond in nitrogen is involved here. So what it can does, it can do is that it can generate NOx, and that NOx when get dissolved in water, it forms the nitrates. So offers a sustainable alternative to Haber-Bosch process, which also wants to do the nitrogen fixation. It can rapidly fix nitrogen at very high temperature, and it is ideal for on-site decentralized fertilizer production from air and water. So this is fairly decentralizable because it is a small portable device, and because it can offer you immediate startup and shutdown, so on-site production is very much possible in this portable plasma devices. Then in the agriculture area, the cold plasmas alter the seed surface properties, and that's how it increases the water absorption and sterilize pathogen. So it can alter the surface properties once the seed absorbs more water, so germination takes place in a much better manner, so you can get more productivity. And plasma catalysis basically combines the plasma with catalyst to enhance certain reactions like nitrogen fixation, volatile organic content breakdown. So those are the areas where plasma catalysis now playing a very important role, but the complete process physics behind the plasma catalysis is still not known. The area is still under active investigation. Now there was one thing, because we are talking about the plasma in industry. Now power supply, constant current power supply, suppose in case of the ARP devices, is one of the most costly components in the setup. The major cost goes in the power supply in such systems. Now whether it is possible to operate multiple arcs using the same power supply, then the cost will be reduced in a significant manner. Like one that is shown here, there are 3 arcs which are connected in parallel, and we are trying to operate using a single power supply. This is positive and this is negative. Whether it is possible. Now look at here, you have given a DC voltage over here, and there is one arc over here, another here, another here. So they are named as DEF. Now you know that it is impossible to make all of them having the same resistance, because when the arc is not there, then it is having neutral gas and the gap is broken. So there is no connection between these two electrodes. The moment you establish break down the gas in between, then only the arc is established and the current passes. So because it is a violent phenomena, and you know this arc has always instability, so none of them will offer the same resistance at a single instant. So suppose out of this, one of them is having some lower resistance. Suppose here, assume D is in figure, for example, the arc that offers the least resistance. So this one suppose offers the least resistance. Then more current will be passing through this, because you are applying a constant current supply. So if current more on this, less will be through this. So where the current is going more, the conductivity is coming from the heating, so it is getting more heated. So more electrons, now conductivity is more. So more current will be passing through this and less current will be passing through them. Now less current means lower ionization, higher resistance. So it will try to push more current over here, because the current will never try to go through a higher resistance path. So current will be further less over here. So ultimately what will happen, that only D will survive and E and F will get extinguished. So this is a practical fact. That's why actually if you are operating an arc device, usually every arc device will require their own power supply. Not multiple arcs can be connected to the same power supply. So that is one thing which is not so encouraging, because we are trying to reduce the number of power supplies, and we are trying to operate number of arcs using the same power supply. Unfortunately, that is not possible. So you need one power supply for one arc device. You cannot operate multiple arc devices using the same power supply. So the problem I have explained why it is so. Now if parallel connection is not possible, whether it is possible to operate them in series like this. Now again you see that the arcs D, E and F, if it is possible to operate them like that, then you need to break all of them at a single instant, because you need to flow the current. If current is not flowing, then arc will not be established, arc will not stay there. So this is the way that these three torches, so this one cathode is connected to another anode, and similar way the circuit is completed, and here it is the schematic of the same system. Now as I told you that if you want to operate all of them, then each of them will have a voltage drop. So D will have certain voltage drop, say delta V, and E will have similar another delta V, this F will have another delta V drop. So when you are operating a single arc, you are supplying a voltage which is only delta V. But if you are operating in series, then you need to supply 3 times the delta V voltage, and that may be really high to be practical. So again you are finding issues if you want to operate multiple arcs in series. The one problem is that you need to break all the gaps simultaneously, otherwise current will not pass and arc will not be established, and breaking 3 different gaps at a single instant is bit difficult to synchronize that way actually. And you need to break all of them using some high frequency together, so that will be a very cumbersome thing. The other thing is that even if it is broken at the same time, then the arc established will require a open circuit voltage for operating that arc, which is very high compared to what you would require if you were operating a single arc. So that is why the design of such power supply becomes again further cost demanding. So this is also not an attractive option. So usually for arc operation you use one power supply, and they are constant current power supply for one plasma device. So now I come to the one numerical. This is our last numerical. This is a hand-on practice on nitrogen fixation system. The problem is that a thermal plasma reactor operating with air, air is having 78% nitrogen, 21% oxygen, and produce NOx gases for nitrate fertilizer. The reactor runs at a flow rate of 30 liter per minute of air, and the plasma conversion efficiency for nitrogen fixation is 90%. In case of thermal plasma devices, this will be different for non-thermal plasma devices. Both of them can fix nitrogen, but this problem is particular to the thermal plasma devices. Now assume standard temperature and pressure, and that all fixed nitrogen forms nitrate after dissolution in water. Calculate the mass of nitrate fixed per hour. So what the parameters that has been given in this problem, we note down here: airflow 30 liter per minute, conversion efficiency 90%, sorry, this 0.012 has come some way, it is not related with this one, so we just neglect this one. Okay, so this figure has been typed by some mistake from somewhere. It is not that one, so it is the conversion efficiency is 90%. You just assume that, you neglect this one. Then nitrogen fraction in air is 78%, so it is 0.78. Molar volume in standard liter per minute is 22.4 liter per mole, that you know. Molar mass of nitrogen is 62 gram per mole. Now, what is there that the parameters that you have chosen, that is 30 liter per minute, is really practical as far as these thermal plasma devices are concerned. So this is a type of order of flow that we usually encounter. Now moles of air that has been considered is 30 liter per minute. So in mole, if you convert, it becomes 1.339 mole. And moles of nitrogen that has been used is 1.339 into 0.78, because it is 78% only, it is your nitrogen. So that figure has been taken in, and moles of nitrogen is coming to be 1.045 mole, when the moles of air is 1.339. So 1 mole of nitrogen is producing 2 mole of nitrate, because N2 and this is NO3. So there are 2 N atoms, so you are getting 2 mole of NO3. So NO3 produced per hour is 2 of mole of nitrogen. Now nitrogen fixed per minute is, they have told that it is 90%, so 0.9 you need to multiply it. So this is the mole of nitrogen it is being taken, and nitrogen fixed is 0.9, 90% of that, so you multiply by 0.9 and it is becoming 0.94 mole. So nitrate that is fixed per hour is 0.94 mole, and you need to multiply by 2, because 1 mole of N2 is giving 2 mole of nitrate. So you have multiplied by 2, and this is per minute. Okay, and if you want to get the figure per hour, so you need to multiply by 60. So you get this product. So this much number of moles are produced per hour, this mole of nitrate. So 1 mole of nitrate is 62 gram. So total nitrate fixing rate, you multiply this by 62, and it is coming to be 6.994 kg per hour. So 6994.84 gram per hour. So it is coming to be around 7 kg per hour. So this is a problem where you are basically using your basic knowledge of physical chemistry, and you are trying to find out in a thermal plasma system what is the nitrate fixing rate. And what you are seeing here, that it can give you around 7 kg of nitrogen per hour, if these are the parameters that are being used. So this is quite a significant rate, I can say you. So, likewise, you can apply your physical chemistry knowledge in many areas of this waste to energy systems, plasma medicine, and this plasma in fertilizer to calculate the basic parameters of the processes. So, I hope that you have enjoyed. From very simple considerations we tried to reach very important conclusions, and the potential of the technology we tried to understand. Hope you have enjoyed the all the tutorials that we have presented. So this finishes the 12th tutorial of this course, and wish you all the best, and you have a great time and a great venture in future. Thank you all. Thank you very much.